Okay, so in today's lecture, we are going to talk about ensemble methods, which is extremely popular methods in practical machine learning. So, so let me just define what is this ensemble method and what is ensemble learning. And for example, if you want to work on very complex problems, and what you do is you outsource this complex problem to thousands of random numbers. And each of that will give them and will give you their answers. And for example, if you want to work with the binary classification problems, so the answer will be 0 or 1. So what you can do is you can aggregate their answers. You get 1,000 answers from 1,000 random peoples. So you can use your rules to using their answers to make your decisions. And a lot of cases you will find out these kind of an aggregate answers is usually better than one specific answers. So that's something called wisdoms of the cloud and the crowd. And this is very important. And you can do very similar things with, and not with random peoples. Instead you can work with a group of predictors. So for example, classifier or some regressors. So what you're going to do is you are going to throw the same problems into various different predictors. It could be decision trees, could be and the logistic regressions, and it could be other like SVM, could be anything like even neural networks. And then you will often find you are getting a better predictions with any single individual predictors because you probably pick the best of the best by using the wisdom of the crowd. But in this case, the crowd is a group of predictors. So this is something called the ensembles. And this whole technique is called ensemble learning. So let's define these things in more precise way. So what we can do is we can consider an L different classifiers. So what you want to do is you want to construct a classifier that actually combines the result from H1, H2 to HL. So basically you have L different classifiers and you want to aggregate, so result from each, and a classifier, and you want to construct and ensemble classifier based on this L different and the results of classifiers. So what you can do is, the simple ways, what you can do is you can just have each classifier vote, then you take the majority rules. Since, for example, we are working with a 0 and a 1, which is binary classification problems, you can take the majority rules, see how many of that I get, and which one has higher percentage to be either 0 or 1s. Then you will output 0 or 1s by using majority rules. And also you can also use different and a classifier for different regions of instances and spaces. So for example, you find out particularly problem, for example, and the logistic regression works better in a very specific region of the problems. So then you can use solely using this logistic regression in that area based on the performances. So this is something that is also can be done as well. But the most important thing is even each classifier that you're working with could be just a very simple excuse me, just a very weak learners. That means it is just slightly better than random guessing. So maybe just you only get 51 or 52% of accuracies for this binary classification problems. But you can still take this ensemble for thousands of that kind of like classifier. It could still get a very strong learner. That means you can possibly achieve very high accuracies if you have enough number of that kind of weak learners in examples, and they will be, and they are sufficiently diverse. That is a chance you can ensemble the weak learners and actually to build a very strong learners. So the successful, the success key, the key to success is actually required diversity, right? So you want each learner to be as much diverse as possible. So sometimes that kind of diversity can be quantified, and usually link it to something called like overfitting, right? So and for the overfittings, so the variances of the generalization error will be super large. So in that cases, you will consider and your result and your prediction has a lot of like diversities. So many times you can think about for that decision tree problems. If we use a lot of like depth, and actually and we will have overfittings. But if I perturb this data a little bit, the structure of my decision trees will be completely different. So you can see this decision tree with relatively large depth of the tree levels is kind of very diverse method. It actually can do a lot of things together. But to be more precise, what is diversity is, that means the classifier should make all sorts of different mistakes. So as independent from one another as possible. So that, that turns out, decision tree could be a very perfect an examples, because if we using a very much subset of data to build a decision trees, it's very likely this decision trees is completely different and only focus on that specific set of data. So, if we assume all these data are drawn in the IID manners, then you can sort of assume, so I have a two independent data set. You can assume this like classifier will make different mistakes because we are working two different independent data set in that cases. So, and it turns out, and our decision trees could be a very good candidacies for these a set of classifier. So this is something, and also called like base classifier as well. And also another way that is can promote or increase diversity is we can have different type of base learners. For example, we can have a k-nearest neighbor, we can have a logistic regression, we can have a naive Bayesian, and so on. And we should train the data set with the various different algorithms. And for example, we can train with a stochastic gradient descent, we can train with a gradient descent, we can train with various different methods. This also can increase the chance that they will make a very different type of errors. And particularly if this loss functions is highly non-convex, because it might be trapped into some other local minimums. If we have enough various different like local minimums, then we have a good picture of this loss functions. This has like result to improve the accuracies of ensembles as well, because you have a good pictures of the landscape of the loss functions. So the diversity is the key for this kind of like an ensemble methods. Okay, so and right here we have to talk about the voting, and we can use the majority rule. So this is equivalent with the following diagram. It's called hot voting. So that means for this one X, we are going to feed in L different and a classifier. Then I'm going to ensemble that. Take the, simple majority rules. That will be my output. That will be my like ensemble learner. If we are working with regression, this will be the uniform averaging of the result of from H1 to HL. So, and you can work with a regression at the same times of the classification for that kind of problems. In the meantime, we can work with the softer voting. So softer and the voting is, I'm not going to treat each classifier equal. If we're using right here, we are using uniform averaging. So basically, we treat each classifier completely equally. But sometimes our classifier will output the probability as well. So this is very important because if my output probability is 0.99, that means I have very high confidence to argue this will be, say, in a class of ones. On the other hand, if another classifier only have 0.55 probability to predict as 1, that means I'm like that classifier has less confidence to say so. So what you can do is you can average out this classifier. Instead of uniformly, you can give the weight to give and more weight to those highly confident votes. For example, for H1, if the probability is 0.99, that you are going to say you can multiply 0.99 as your weight, like when you do this ensembles. This gives extra weight for those highly confident votes instead of those with only 0.55 that has a less confidence with that. So after averaging, you are getting this ensemble result as well, and then you output your predictions. So this is also very, very important. So this is a simple, just something called soft votings. So let me show you this hard voting and the soft voting techniques, tricks right here. So we're going to using the same data set that we have, used right here. So this is a moon data set. So you have a 2 moon, and it's obviously not linearly separable. So what we do right here is I'm going to create this voting classifier of 3 different like base learners. I have a 3 base learner. One is logistic regression, one is random forest. We're going to talk about random forest later, and another one is SVM. Okay. So what it did for this voting classifiers, it will clone each estimator and fix the clones. And also this like original estimator will be available through this attribute if you want. And you can just find out all these informations for each base learners. So what you do is you create this voting classifiers, then you fit this X train and a Y train. So we create, by default, that will be a hard voting. By default, we are creating 3 base learners, and I'm using hard voting to make the prediction for that. And you can see for each of that and each learner, on the testing data set, we are getting 86%, 89.6%, and 89.6%. So they have like a slightly different variation here. However, if we make a prediction for the first data set, which is the x text 0, my voting classifier actually predict to be 1, right? But however, what you do is you can actually explicitly to see what does each like estimators predict for all three of that. So what you can do is you can call this predict for each classifier in, this voting classifier's estimator. It will actually output the predictions. For example, for the first data and of my test set, my so my my logistic regression and random forest actually predict as 1. My SVM predict as 0. So by majority voting, these two as and we have 2 of the learners predict to be class of 1, and 1 learner predicted to be 0. So that's why it will be predict as 1, because we are taking the majority rules. And of course, we can check with the result, which is truly to be 1. So, that actually matches. But think about if we are just using for SVM, that means it will predict as 0. Then in that cases, it will be predicted wrong. But fortunately, we have other 2 predictors and the classifiers, and to make this prediction correctly and outbid the result of the wrong result of SVM. Then we tested this data set, X test and Y test, with this hot voting and the classifiers. The accuracy that we get is 91.2% of accuracy. And we can also do soft voting as well. Usually soft vote and voting will achieve higher performances because, as I said, in soft voting, it will give extra weight to those highly confident votes, which in a lot of cases will have the higher and has a higher probability to be correct. However, in SVM, the default predict probability function is set to be false. You need to manually turn it on. Then you say, I want soft voting. I'm going to say dot voting equal to soft. Then you do the fit and the testing. As a result, you got 92% of accuracy instead of 91.2% of accuracy. So you can see this is actually doing a better job with the soft voting. Okay, so on the next, here we are talking about votings, but we can, but we are thinking about having different models, but apply on the same data set. But for example, can we change things a little bit? So we can use the same model, but we are training on a different random subset of the training set. So basically, it's kind of like different level of randomness. On voting classifier, we are having the same data set, but with the different models, right? For example, logistic regressions, SVM, and so on. The model is different. The algorithm is different. But and the classifier is different. But we can have to use exact the same predictors, right? Say, or the same type of predictors. For example, we only use logistic regression. or we only use the Zen tree. But we train them on a random subset of the training set. So we have a whole bunch of data, but we only use a small subset to train it on. And also, how we sample this training set is quite important, right? So what we can do is there are two different versions of doing so. One is we can sample each of training set with the replacement. So that means I sample a point, or sample a data point, and then I put it back, then I redo this again. So that means if we do this kind of sampling, I mean, it's possible that I will be two or more data point has exactly the same data point. So this is called a bootstrap sampling. So as a sample with and replacement. If we sample those like random subset with the replacement, and also we use all the features. For example, if we have like D features, we use all of that. So this is called bagging. Bagging is short for bootstrap aggregation. However, if we're using the sampling methods without replacement, so that means once I sample this point, I'm not going to sample it again. So yes, this will create biases for sure. However, I mean, this is also a very common way of doing that. So this is called pasting. Okay, so at last, if the sampling is performed with the replacement, in the meantime, we are not using the whole feature. We're only using partial feature. So this is additional randomness on a data set. So that means not only we sample the random subset of the training set, we also sample the random features on those random subset. So this is called random forest. So this is and the difference is between bagging, pasting, and a random forest. Okay. So as I said, both bagging and pasting allow this training set to be sampled multiple times across the multiple predictors. I don't think that's bagging. That's bagging in a random forest. Oh wait, to be. Yeah, that's right. Pasting, right. But only bagging will allow the training instance to be sampled and multiple times for the same predictor. So that means, I mean, it's possible for that single predictors, I may have two identical data points. I mean, in the case of bagging. If all these predictors are trained, I mean, the ensembles can make a prediction for this new instances just by simply and aggregating the prediction of the predictors. And it could be like just a hard voting. I mean, it's very likely to be a hard voting. Just take the majority rules. If we work with the regression, then we just take the average for the regressions. So each of this individual bias will have very high bias, and each of like individual predictors will have high biases if we train the whole and original training set. This kind of like and the techniques to train on a subset, like random subset, actually reduce both biases and the variances at the same time. So which is really good. I think we have talked about an overfitting and underfittings in the previous lectures. It's really hard to reduce overfitting, the bias and the variances at the same time. So usually the trick that we do is we take this kind of aggregations. Aggregation usually can reduce both biases and the variances. So as a result, if we take this ensemble methods of like to be trained on like various different random sets on the training set, usually this has a similar biases than those trained on the whole data set. But it will have significantly lower variances than the single predictors to train on the whole data set. There will be proof and why this is true, but we are not focusing on that. I'm just stating the fact, just tells you how we can reduce the bias and the variance at the same time. The best way that we can do is we take this aggregation methods, right? So this is also a very commonly asked questions during data science interviews. So, and what we can do is we can do this bagging classifiers. So, and what I can do is I'm going to create 500 decision tree classifiers without specify any depth of the decision tree. So that means we surely will know this will have overfittings, but that's okay. And for each decision tree, I'm going to randomly sample with replacement of 100 training instances. So we create 500 trees to train on 100 random and data as a subset and a subset data of the whole data with the replacement. So we create this baggings. So we can plot out this whole decision trees with the baggings. You can see this is very, very significant. If we don't do any kind of regularization, this is the decision trees boundaries look like. And you can see this is not doing a very good job. You have a lot of zigzag and a lot of unnecessary zigzags. So if you have a new data coming in, it's very likely it will show the overfittings. However, if we have a bagging, you can see right here, it has a very smooth moon shape separations of these two data sets. Although they have some training error, but we are sure if we have a new data coming in, this decision boundaries, it can actually separate these two data sets very well. That's exactly a human beings will do if they're asked to draw a curve to separate these two data sets. So you can see the power of the backing right here. Okay, so another thing is during backing, so this is basically some training and a data set and could be like sampled multiple times for any given predictors. So that means even you sample the number that is exactly the same as the whole data set, you might not sample all the data set at all. In fact, we can show later only 63% of training instances are sampled on average for each predictors. So that means there will be remaining 37 of training instances are not samples. So this will be naturally being the out of bag OOB instances. But I want to emphasize if for one simple and for the first decision tree, you will find out this 37% of the data are not sampled for the first and the decision trees. That will be not the same 37% instances for the second decision trees. So that means they are not the same for all the predictors. Okay, why 63%? So here is a very little proof why this is like that. So if we have to draw a one instances of a data set, training data set of size of M, and obviously that, and each instances will have probability 1 over M get picked. And of course, that will have 1 minus 1 over m of not getting picked. However, if you draw like m instances with replacement, all these draw will be independent. That means each instances will have the probability of power of m of not getting picked. So if you look these things closely, this actually, so has a limit. If we let m goes to infinity, this limit we can calculate will be exponential of -1. So this is because the definition of exponential x has the limit of the following like that as m approaching infinities. If m is really large, this actually has close to the limit of 0.37. As a result, 63% will be sampled. But still, there will be significant amount of data will never be sampled if we choose the bagging strategies. So what you can do naturally is this bagging, like Ensemble, can be evaluated using this OOB instances. So that means if we using the bagging techniques, we don't actually need to have a separate validation set. If we have enough like estimators, each instances of training set, we're likely to have some like instances for several estimators. So that's why this naturally can make fair predictions for this kind of generalization errors, because we want to using that kind of validation set to predict, to estimate the generalization error. So this will be a good way to say, if you're using bagging strategy, there's no need to separate a validation data set, because you can naturally using out-of-bag instances as the validation data set. This is also commonly asked questions in data science interviews, whether you need a validation data set in this bagging ensemble strategies. The answer is no. So what you can do if you want to using this OOB evaluations right here, what you can do is you can just turn on this OOB score to be true. Then you can like evaluate this OOB scores immediate. This will actually give you 92.5% of accuracy on this validation data set, which is quite good. And that actually and reflect this like generalization error, which is quite close. I want to remind you, this is quite close to on this testing data set, which is 92% of accuracies. So you can see our validation error actually perfectly reflect the errors of testing errors, which is like an approximation of generalization errors. Okay, so you can see right here, this also gives you some OOB like decision functions right here. This is the probability for the first 3 instances, right? So you have like 94% to be 1. This one is only have a 96% to be 1. Then for the third one is, we know this is perfectly to be 0. All right, so, oh, I think I was wrong, I'm sorry. This 92% is I'm using this voting strategy, I believe, with the softer votings. This is bagging, so we haven't tested on the testing data set. If we actually test on the testing data set, we are getting 90% of accuracy, which is also quite close to 92.5 right here. It actually has a good reflections on the generalization errors. So which is good. So this is bagging. So I haven't, talk about pasting, but pasting is basically very similar. But the difference is in pasting, they don't naturally have this out-of-bag evaluations. If so unless you're like random and a subset is significantly smaller than the whole data set. Unlike what we have for the out-of-bag evaluations of the baggings. So that's why so in any cases, bagging is a better strategies than pastings. It's like with replacement and also you sample the data in a true IID manners. And in the meantime, this naturally has OOB instances can be used as the validation data set. Okay, so for the random forest, it's basically trained through the bagging, which means it's sampled with replacement, but and typically with the maximum sample set to the size of the training set. So that means although we set the maximum samples set to be training set, but the actual data here, we're still having the random subset because we are using the and the replacement strategy. And also what we can do, and that is different, is we don't just taking the whole features. If we have 10 different features, I only take a subset of features. This can further introducing the randomness. With introducing further randomness, it can make our like an estimators even more diverse. So the more diverse, the better, as we can see right here. So that's why, in some senses, random forest is doing better job than bagging. So we are creating even more and more and diversities. So here we are using this random forest classifiers, and of course you can using random forests and random forest regressors for the regressions. And this is basically says I'm going to create 500 decision trees, and each limit the maximum leaf that we have and leaf nodes is 16 nodes. That's the best and the maximum nodes that I'm imposing. This actually naturally create the restrictions or constraints or regularizations of decision trees. So we do the same thing. We do the fitting, we do the predictions. We're getting 91.2% on the testing data set. Of course, you can rewrite baggings as well to rewrite it and the random forest. The differences here is this random forest, we are taking only partial features, right? Here what we are doing is, in theory of the random forest, it actually only take about square root of number of features. And for example, we have 9 features. We are only take 3 features out of 9 as maximum features that we're going to handle to create this decision trees. So this is the default setting of random forest. Of course, you can change that. So these two actually will be completely equivalent in the cases. Okay, so in fact, this random forest, I think we have a talk about this on feature selections in the videos. There are 2 different methods actually can select the features. One is lasso. We have talked about that in the previous videos. Another one is the random forest. And I also demonstrate that. But there are a bunch of like theory and how this actually being done right here. I want to emphasize that on a separate matter here. So basically, in the case of like a random forest, so the whole idea is the closer the mean position of a feature over the trees to the root, the more significant it is to this classification problems. So think about, I have a decision tree right here. If that feature is closer to the top or to the root of my decision trees, that indicate that will be my first splitting criteria to consider. So that also gives me indication this feature is more important than other features. So, and also what does that actually means is so actually if we split on this particular features, it actually has a gain in something called Gini impurity. That means it actually measures at each split in every tree is a measure of importances that directly associate to this splitting features. The value of this scores is different, right? For each features. So that means we need to add them up for each of features. Say we have a 100 trees, and each tree is trained on sub data set on sub features. And then for each tree, they have a different features and on the different splitting node right here with this and Gini impurities associated to each of features. Then I'm going to accumulate of all the results of the scores together for each of tree, for each of features. Then I'm going to using this information to calculate the feature importance. Okay, so there are two different ways to assess that. The first way that I'm going to do is something called permutation importances. That's, in fact, not used in a scikit-learn. There are other methods that, as I mentioned, is to using the Gini impurity here. Sorry, I think and scikit-learn use slightly different methods. We're going to talk about this as well. So this is all the details right here. So, and then there are two parts of that. One is this permutation importance. Another one is the random forest feature importances. Okay, so these are two different parts and two different methods. Okay, so let me just get into this detail a little bit. And then this is also very important. I know this is a little bit too quite detailed, but it's completely worthwhile to study as separate matters. So basically, and I want to remind you, and what we can do is we can using this auto back error as a measure of redundancy inaccuracies. So what we do is, the greater of the redundancy inaccuracies, the higher the score it is. So what we do is very simple. So we have a bunch of features. For example, this is the examples right here. So what we do, I think that's wait. Okay, so this is the feature right here. And for example, what we do is, let's say this is the feature I'm x2 right here. That corresponding to the instances of 2, instance of 4, instance of 5, instance of 7. Then the corresponding feature will be 2, 3, 5, 7. What we are going to do is we're going to shuffle the order of x2. So it actually becomes 5, 7, 2, 3. So that means they are no longer having the one-to-one matchings to the second, fourth, fifth, and the sixth instances to the feature of x2. So that means I'm actually permute the values of x2s. Then I'm going to make these predictions to see how much and how much the redundancy and the reductions of my accuracies. The more of reductions, that means that feature is more important, right? So that's what I mean, this sentence is right here. The greater the redundancy in accuracies due to the permutation of the variable, then the higher of the importance scores. So that means, in general, variables with average greater and redundancy in accuracies will be more significant for the classifications. So the rationale is very simple. If you randomly permute specific variable, then the original and association with the y is broken. That means when these like permuted and the variables together with all other like features that we have is used to response for this auto back and observations. If the prediction accuracy decreased significantly, that means this feature xj is really, really important. If not, then that means this xj actually contains less information or not much information, or even worse, could just be considered as a noises. Then this feature will not be important. So we do all these things with all the trees, with all the features. So that means so you think about I have like two for loops, and one for loop is I need to loop through all the trees. And for each tree, I need to loop through all the features, which is xj. J is from 1 to d. D is the number of features that we have. So what we do right here, you can see this is basically the accuracy before the permute of the feature of xj. This is accuracy after permute of xj's. So usually, if we have enough data, my accuracy will decrease. So how much it actually decreases, that will be my permutation importances. Okay, so, and of course, these of that is not normalized. So what you can do is you need to normalize it and average that with all the trees. And we have n different trees that are going to add all these permutation importances and then divide by n. And of course, sometimes we can and normalize by the standard deviation as well. So this will be your permutation importances with the feature of xj's. I have examples right here. It's very, very detailed examples. You can go through these examples with a specific tree of, I believe, tree of 1. So basically, this is a very simple examples. if you take the bootstrap examples, in fact, you are getting, wait. Oh yeah, and you are getting, these will be your training data, and as the result, the rest of the data will naturally be an out-of-bag examples, will be naturally being the validation data set to test the feature importances. You train everything right here, but you are going to test that on the out-of-bag examples. So basically, we have this out-of-example and the back examples will be 2, 4, 5, 6. And say you want to compute the permutation importances for the X2, then what you do is for each of the out-of-bag examples, we compute accuracies before and after permutations of values of X2. So this is before the permutations. We have 2, 3, 5, 7 for those 4 out-of-bag instances. And this is after the permutations. It becomes 5, 7, 2, 3. We basically reshuffle that. And then there will be no correspondence between X2s with all these and out-of-bag examples. As a result, we are going to make the prediction by using the same tree that we trained on the rest of the 6 data points. And we find out the accuracy decreased from 0.75 to 0.5. So that indicates the differences is 0.25 is the permutation importances for the tree 1 and the feature X2. Okay, so but you have to work out for all the feature, which is X1 to X4, and all the trees from tree 1 to tree 5. So that means you have to repeat this 20 times, right? So that's a lot of work to work on to calculate all these feature importances. Then for each feature, you have 5 different trees. Then you ensemble that together. Right, so then you will have the feature, importances for 4 different features from X1 to X4. All right, so but that's not what the scikit-learn is doing. Scikit-learn is actually using the Gini impurity. It's slightly different, but the whole idea is quite similar, though. Let me see right here. So let's look at this like very specific examples. And with examples. So basically, this scikit-learn is slightly different. And for example, the more information gain that we have to split this features, then the higher of the feature importances. And here, what we do is we are using the Gini impurity as kind of measure of the information gain. So that means we are going to calculate this Gini impurities and compare with the one with original node L and with the childs as well. So this actually is the whole theory underneath of that. So this is basically the and Gini, so Gini impurity, yes, and this is impurity of the node right here. This is the Gini, so impurity on the left branch. This is the Gini impurities of the right branches, and according to the weight, and it has to be like weighted numbers of the samples. And reaching to the node Li. So basically Li is the left children or left branch, and Ri is the right branches. So what we do is we are calculating this redundancies in impurities. It's and then so this is being like doing the Ri right here. So and you have this Ri IT. So and I is that like specific node of I. T is the number of the trees that we have. Then what we do is we need to calculate this kind of and feature importances for specific feature of J and the T tree. So basically, I need to sum up all the nodes that this node actually split with using this feature of J right here. So this is, I'm going to sum all these redundant and the reductions in like Guinea impurity right here, then divided by all possible node of redundant and reductions in impurity right here. So then we divide these two quantities. So this result will be the feature importance of the feature J's for the tree T right here. But in the meantime, we have a lot of trees. Then we need to sum all possible trees from 1 to the n. Then we need to take the average of this. So this will be my average features importances around all trees in ensembles. All right, so we can do all these kind of things. This you can go back to check. It actually can give you very specific and examples with iris data. So this is all the features. And for example, for the first tree that we have right here, and it actually separate on the sepal length. So and the point of separations is 5.75. That's the first node, and which is my root right here. Then we have two node and the right and the left. So we calculate the redundancies for the right and the left. Then we calculate all these values together. And this will be my and this will be, and the redundancy of an impurity will be 0.2 right here, and the redundancy of SL2 is 0.00, and which is very small. And you can do very, very similar things for, and this is sepal length 1, this is sepal length 2, and you can see right here, and the first time that we see the sepal length 1, I have a lot of and redundancy and reductions of the impurities. On the second time that we have the sepal length features, and reduction and of the impurities is super small. So we need to add them up. And also, and we can do the similar things for petal width and the petal width and the petal length. So and we can see in this cases we are and have to reduce of 0.035 and the other ones as well. So you can sum all them together. This will be your feature importance right here. We don't have a sepal width here because it's never being used. So that means it's 0 right here. So you can see from this table, my sepal length is it's more important. Oh, sorry, the petal width is more important right here. Then you can do the similar calculation for the second and third trees, then we can average the result in total. Overall, you can see if we average the tree 1, tree 2, and tree 3, these are the 4 different features: sepal length, sepal width, petal length, and petal width. We find out the most important features that we have is petal width, where the feature importance is up 0.47 right here. All right, so you can actually calculate the random forest feature importances. You can see it actually match those values perfectly. So this gives you some idea how we calculate these quantities, and we're using analytical method to calculate by hand. In the main so in the meantime, we can compare this result for the feature importances in the random forest. Okay, so since we have been working on this synthetic data in the past couple examples, let's try some practical data set. So this is data set actually from the survey given the visitors of hostel listing on the booking.com and TripAdvisor. These features are average ratings of different categories, including service quantity and service quality, room condition, value, money, and so on. At the end, we want to predict the hostel's overall ratings on this website. So what we have is these are all the features that we have. At the end, we want to predict the ratings. So this will be my target. Then we can, using this like random forest and a regressor, we are using 1,000 of the maximum features. Sorry, so we are using like 1,000 and it is in trees. And the maximum feature that we choose is 10, and which is all of that. But I think with the yes, like and then the maximum features that we choose is 10. Then we drop out this rating, which is my so my predictions. Which is my target. Then we're going to fit the data that just calculate this importances right here. With these predictions, it can tells you right here the most important things is actually the staff, value for money, and sheer space conditions. So that means customer actually pay great attention to staff and the price quality ratio, which is the value. This means it will actually affect the rating the most. And you can see all these differences between these features and other features not very large. For the other features, for example, the extra services, general conditions, and the convenience, they also contribute significantly. We can basically conclude that if we exclude any of these features, will lead to significant reductions of the accuracies. So that means and in order to make a good predictions for this model, we need to include all 10 features together. But as a very crude analysis, that means if we want to, if the hostel want to have a better rating, the main focus should be on the staff and the value for money. If they can do better on these two categories, then there will be higher chances or higher possibilities the host will get better ratings. But of course, even though we want to using all 10 different features to make the models, that will be much more detailed analysis. With this feature importances, it just gives you a very quick and a crude analysis, which features are the most important ones that you should focus on. You can also work that on the MNIST data set as well. This will take a little bit while to run. And from here, it basically says I want to using the random forest of 100 decision trees on the MNIST data set. Then what we do is we are get this feature importances. Then I'm going to reshape this into 28 by 28. That means that and as I want to give a plot on which pixel it's more important and which pixels of the image is less important. As you can see with our feature importance is coming from random forest, most of the things inside of this images is very important. Everything on the edge of images is not important. Sometimes it's less important, which fits to our understanding on the MNIST data set, because we know for the MNIST data set, everything on the boundary is not important at all. What is important is everything inside, in the center of the images, because all the digits are in the center of the images. So this also verify our idea or our intuitions to those MNIST data set. Overall, you can see this ensemble methods, particularly for this random forest, actually can provide a very good methods to pick up the features for feature selections. So that's why you could use maybe a sub data set to play with before you work on the full data set. Using this sub data set and to run a simple random forest and to calculate all these feature importances, then you will see which features are more important, which features are less important. But think about it, you have maybe 30 or 40 features. This strategy can narrow those features into significantly smaller portion, maybe less than 10. With only 10 features left, then you can maybe think about various different feature engineering strategies and even create more relevant features for that. So this is various different strategies that you can impose to build the best models that you can think about in the practical data set. On the practical data set. In fact, in the later of the homework, you will be asked to do these kind of feature engineering and to select the feature, to create more features through feature engineering, and to ensure you are working and you get out the best result of the models. All right, so that's everything I want to talk about today for this ensemble methods. In the meantime, I'm going to, the next video, I want to spend maybe 10-15 minutes to quickly go over and worksheet and case study and on how to using this kind of cross-validation methods to actually find out the best parameters for this type of ensemble methods, which I think is very, very important in practice. All right, that's all for today.